Okay, so we've got pressure vessel here, hemispherical ends, and we are going to go ahead and have it have cyclical loads applied to it. Now, obviously, you need to do your analysis on the pressure vessel itself, similar to what we did last semester in 233. That had been said. Right now, we're going to be worried about the bolts that are used to attach the hemispherical ends. So we got some mating flanges that are built in here. 2.5 millimeters thick steel each, and then they're gonna have a gasket in the middle. Gasket's gonna be like a full gasket, so taking up the entire cross section of the mating flange, basically, and that's going to be 0.5 millimeters thick, using a material that has a Young's modulus of 500 megapascals. So, obviously significantly more flexible than steel is. And then the tank has an interior diameter of half a meter, and we're using 16 bolts per end here. So basically, if we want to have a safety factor of 2.0 versus leakage, so basically an ability to have increase it to 2 megapascals without any leakage. And we also want to have a 1 point of safety factor of 1.5 with regards to the failure of the bolt for indefinite life. So of course, obviously, it's a fatigue safety factor. What sort of size of bolt would we need for a class 8.8 bolt? Um, we're going to assume here that we're starting with an initial loading of 70% of the proof strength of the bolt. Or, we may possibly load it up to 90% and then, assume that there may be a bit of initial loosening that goes on, but we're still maintaining a reasonable amount of that a reasonable amount of that tightness to start. So 60% of the proof strength of the bolt. So essentially, we have a very high Young ratio between what the Young's modulus of the tank it is and the Young's modulus of the gasket. What that means is that we're going to have the effective stiffness of the joint, of the clamped section, is going to be dominated by the stiffness of the gasket. It's the least, it's the more pliable member that has the highest effect upon that. So I'm going to say again, to approximate that, let's assume that all the load is carried by the bolts. So when we start off with, we're going to start off with our initial tightening, and we're going to increase, we're going to pressurize it, which is going to increase, it's going to apply an external load to the joints, which for most for joints that, if everything here was steel, then typically speaking, you'd see a bit of an increase in the tension in the bolts, but most of that load would be usually carried by a decrease in the clamping of the of the joint, a decrease in the clamping force. But we got that gasket there. Because we don't really want a decrease in the clamping force. We want to keep that. We want to keep whatever hazard, whatever gas it is that we're trying to contain inside that pressure vessel needs to be contained. So we're going to want to ensure it stays there. So that's what the gasket's for. So when when that gasket deforms, it does so in a relatively flexible manner, at least compared to the steel. So it does so in a manner that will transfer the bulk of the load to the bolts. So let's just assume that they carry the entire thing. So the load per bolt, let's assume that it's based upon the maximum pressure. Sorry, the load per bolt at the maximum pressure. Again, that's just going to be how much force is going to be applied to those ends, the hemispherical ends, and divided by the number of bolts. So again, the force is going to be proportional to the cross-sectional area and the pressure. So the maximum pressure is 1 megapascal, and the cross-sectional area there can be found as pi over 4 times the diameter squared. So 1 megapascal times pi over 4 times 0.5 meters squared divided by 16 volts. So that'll give us 0.0123 times 10 to the 6 pascals times meters per second times meters squared per bolt. Obviously a pascal is a newton per meter squared. So those two things, that'll cancel out to newtons, and then I just, obviously here put it in as kilonewtons. So 12.3 kilonewtons per bolt is what sort of force is going to be needed to restrain that end from popping off. All right. So we'll go look at our material properties for our bolts. Again, we're looking this up in the table in the textbook. So it's or table in the slide notes would work too. But our ultimate strength 8 to 38 megapascals, yield strength 660, proof strength 600 megapascals. So we know that this is a fatigue problem, so we're going to have to go ahead and figure out what our SN is. So again, as per usual, we're getting information from 8.1 of juveniles, table 8.1. So our SN prime is half of our SU, so 415 megapascals. Our loading factor, this is axial force we're applying, so 0.9. Our CG is going to be, they give a value within a range of 0.7 to 0.9. Again, I usually like to kind of err on the default to picking kind of the smallest value in that range, kind of the worst case scenario. And this was the range that was given for, I believe, 10 millimeter to 50 millimeter bolt, members, basically. So it would apply to bolts, it would apply rods, or what have you. So obviously, if we end up calculating a required value for the diameter that's significantly larger than that, then we may need to revisit that. CS, we're not actually relying upon the table here. CS, we're looking here is 1. And again, that's basically because for bolts, you're also looking up the fatigue, your KF on the little table there, and they kind of basically kind of already built the CS into the KF, basically. And then for this instance, again, the problem didn't specify what sort of reliability you wanted, but typically speaking, for pressure vessels, you should want at least a fairly decent reliability, because again, failure is fairly catastrophic. So I'm just going to assume 99% reliability, and then so that'll be 0.814. So take that stuff, multiply it together, and we get ourselves 213 megapascals. Okay. So from that, we can calculate what our SBA max is. Now, again, just a reminder. Here, I'm going to scroll down so I can sketch a little bit. That's because when we are working with a bolt that is fairly high, loaded up to a decent amount of its decent amount of of its initial load, then especially once we kind of take the stress concentration factor into account, we're basically working in an area where you're always going to get localized yielding. So, we're kind of starting like here, and we're loading it up like this. So we're always getting that localized yielding going on, which means that because of the localized yielding, due to the stress concentration factor, what we're getting is some residual stress. So the residual stress is a residual compressive stress, which has a tendency to move the basically shift the line back. And you basically shift the line back such that your failure point actually ends up being where this intersection occurs. So that's what's going on there. So our failure, the shift of the the residual stress causes a shift such that our intersection is basically all such that our actual failure criteria is kind of irrespective of the initial mean stress that we had induced there. It is or SN. I was using SN for that, wasn't I? SM, SA on this side. So it becomes just a function of our SA, basically. So anyways, and what values we were looking at for that. Come on. There we go. So our SBA max, so the maximum amplitude of the stress in the bolt for failure, is calculated just based upon the SN, the SU, the SY. So plug in those numbers in there. That gives us 58.7 megapascals. So again, that's going to be on this chart here. That'll be this value right here. That'll be that magnitude right there. So that's basically the expected failure criteria. So if we expect failure to occur at that value, then we can figure out what sort of value we can work with by dividing by our safety factor. So we take our 58.7 divided by 1.5, that gives us 39.1. So we can see an amplitude of the 39.1 megapascals while still having a 1.5 safety factor with regards to fatigue. And next up, we got our so that's our SBA design, and of course that is again equal to our fatigue stress concentration factor times the amplitude of the force in the bolt divided by the thread area. So if we know that if we're working with the criteria that when we're loading and unloading, all the load gets its way to the bolt, then basically what we're doing is, we're starting out with an Fi, and then we're increasing and we're decreasing, increasing and decreasing. So we're doing something like this, where this difference here is equal to the FE. So the amplitude of that increase and decrease parameter, that's going to be equal to the FE divided by 2. So that's for our loading condition of 0 to FE. So the amplitude of the load that the load that the bolt sees is 6.15 kilonewtons, and so right now we know this SBA design. We know that FBA. We're trying to find the size of the bolt. So basically, we're trying to find kind of the minimum stress area, the threaded stress area. So we're going to need to know what the KF would be. Again, we got that chart. Just 1 second while I find. Let's see here. There we go. So we got this. We got this chart here. If we're working with again relatively strong bolts, 8.8 and above, we're working with 8.8. Then if we're using cut threads, it's 3.8. If we're using rolled threads, 3.0. It didn't say yet, so let's assume we're working with. Let's go ahead and assume we're going to be working with rolled threads. That's not an unreasonable assumption for dealing with if we're trying to keep a pressure vessel safe, especially if we're talking relatively large bolts, which this may or may not end up being. Those are more likely to be rolled than the smaller bolts. So we got that KF of 3.0, so we can solve for the AT. So this will give us basically the minimum size of the threaded stress area that we'd be able to safely hold that load with. So 3.0 times 6.15 kilonewtons divided by 39.1 megapascals, 0.471 kilonewtons per megapascal, or 471 newtons per newton per millimeter squared, gives us 471 millimeters squared. So again, we're going to go look up what is suitable on our charts. Look up a suitable size for like a thread that would work for that. So let's see here. So if we're looking for a fine thread, 27 millimeters across would work. That's 496 millimeters squared, or a coarse thread of 30 coarse threaded 30 millimeter would also work. So for the time being, either of those would work. Let's go ahead and stick with the smaller one. We'll stick with the smallest size one that we can kind of make it fit, because again then we can kind of make the flange smaller and so on and so forth. If this ends up being kind of a bit too large for your purposes, then obviously I think the ideal thing to do here would just be to increase the number of bolts, so you're sharing the load more. You might double it again to go to 32, bolts. Just put another bolt in between each bolt that you have, if you got enough room between the bolts, and so on and so forth. But at 37 an M30, sorry, an M27, not 37, M27 X2 bolt will have a large enough thread area to meet our purposes. So we're also going to have a look to see, does it meet our leak requirements? So for one thing that we need to do is basically figure out what the effective cross-section area of the clamped members is. So when we're clamping the stuff between, if normally when you have like just metal on metal contact, you've got a conical spread of the joint. But when you got one section where it's metal and another section in the middle where it's a far more pliable, then it's usually a more reasonable assumption to assume that you're not getting any significant increase in the size of the kind of the cross-sectional area in the middle. So you got this conical spread here, and then kind of straight walls down here. Honestly, realistically, it's probably not going to make too much of a difference if you assume that the conical spread continues into the gasket, but it might. It's going to be a bit more accurate to do this way. But anyways, so our D1 term, again, that's going to be roughly equal to the nominal size of the bolt, the 27 millimeters. We're not drilling our holes significantly any higher, any larger than what we need to be for this purposes. The D2. Oh wait, no, D2 is supposed to be. I drew it wrong on here. So D2 is from. I'm going to draw it in red here. D2 is this distance here. So basically, the distance for the where basically the spreading starts. So that's basically a function of the size of the head of the bolt and the size of the nut attached. So those are typically speaking going to be on the order of 1.5 times the nominal diameter of the bolt. And then our D3, kind of the maximum value. Again, that is basic. That size there is going to be basically based upon if we had just had a conical spreading section without that gasket in the middle. So based upon grip size, I've got 2.5 millimeter flanges on each side. So based upon kind of a total grip or a total joint length of 5 millimeters. So D2 plus the 5 millimeters times the tan of 30. So that'll give us 43.4 millimeters. So we can use that to figure out kind of the effective cross-sectional area of the gasket and the effective cross-sectional area of the steel flange. So the effective cross-sectional area of the gasket, again, we're not assuming that's spreading, so this is basically the cross-sectional area of kind of this little disc in here with the hole removed from the bolt in the middle. So pi over 4 times the outer diameter squared minus the inner diameter squared. That'll give us that'll give us 907 millimeters squared. And then for the steel flange, we expect it to be slightly smaller than that because again, it's the effective area for the gasket is entirely contained within within the base of the conical section of the steel portion. So it's certainly going to be smaller. But again, we plug it into this formula we had here, the d squared plus 0.68 times dg plus 0.065 times g squared. So plug in the number values in there, we're getting 822.4 millimeters squared. So again, a reminder of what the kind of the K in general would be. That's the cross-sectional area times the Young's modulus divided by the length. So if we're kind of going to try to combine it for the different materials, the overall, the inverse of the overall is equal to the sum of the inverse of the individual components. So 1 over the 900. So the AC for the gasket is the 907 millimeters squared times 500 megapascals divided by the 0.5 millimeters. That is its length, sorry, thickness. The AC for the steel portion of the flange, that's the 822.4 millimeters squared times 207 gigapascals, or 207,000 megapascals divided by 5 millimeters squared. So based upon that, we end up adding up, taking the inverse of those. We get 1.102 times 10 to the negative 6 millimeters per Newton plus 2.9 times 10 to the negative 8 millimeters per Newton. So, adding these two up, you see that we're really dominated by the size of, by kind of the stiffness of the gasket there. It's the gasket there is only taking up 5 millimeters versus 0.5 millimeters versus the 5 millimeters of the steel, but it is so much more flexible than the steel that it really dominates. So adding those two values up, we get 1.13 times 10 to the negative 6 millimeters per Newton. And then just taking the inverse, we get the Kc for the clamped section itself, 883.7 times 10 to the 3 newtons per millimeter. So the effective cross, essentially, we've got a certain amount of stiffness that we would have had if we just had the gasket, and then adding the steel gives something else that can also deform a little bit more. So we're reducing the stiffness so the stiffness of the overall joint is going to be slightly smaller, but not that much smaller than what just the stiffness of the gasket would be. As for the stiffness of the bolt, again, its cross-sectional area times its Young's modulus divided by its length. So we're using the 5.5 millimeters because, of course, the bolt is gripped between both the gasket and the steel portion of the flange. We're using the area because we're based upon the nominal diameter of the bolt because this is occurring primarily in the stretching is occurring primarily in the shank section of the bolt. And then, of course, the 207 gigapascals. So once we get our units converted, that ends up being 21.5 times 10 to the 6 newtons per millimeter. So we got that. Stiffness, we know that if we want to figure out, our initial tightening comes into play too. So the problem stated that we were operating at, in the condition when the tank was unpressurized, the bolts were still at 0.7 or 70% of their proof strength for terms of tension. So again, they might have tightened it a bit more than that in the beginning, and maybe we expected a bit of loosening, or perhaps that's all they tightened it up to begin with. Who knows? But translating that into force, 0.7 times the proof strength times the threaded stress area. So 0.7 times the 600 megapascals, which was our proof strength, which we saw before, and the 496 millimeters squared, which was the threaded cross section, the stress area of the threaded section for the 27 millimeter fine threaded bolts that we had selected. So that gives us a pretty large value there. We're working at 208 kilonewtons once everything is said and done. So when the load's applied, the remaining clamping load is equal to that initial load minus this ratio of the Kc and the Kb's times our safety factor that we're kind of trying to design for, and Fe. So again, if we want a safety factor of 2 with regards to leaking, that's basically us saying that, okay, if we accidentally load this thing up twice as much one time, is it going to burst? So the effective load would need to be twice as much than our Fe. So we get 208 kilonewtons minus this ratio here. It's just plugging in a combination of these two values that we have up here times 12.3 kilonewtons times 2, which ends up dropping the clamping force down to a measly 207 kilonewtons. So we're not even close to opening. This thing's still clamped quite tight. So our failure criteria in this condition, for this particular setup, is certainly dominated by the fatigue strength of the bolts. Fatigue is going to be a lot more worrisome here than the possibility of leaking. And that's largely due to the fact that the gasket that we're using is relatively pliable. But yeah, there we go.